now that we've covered that acid-base reaction largely really just only depends on enthalpy, because there's no entropy difference between the reactants and the products, right? So it only depends on enthalpy, meaning that acid-base reaction is really easy to predict because it's only dependent on one factor, the enthalpy. If the products of the acid-base reaction seem, if they are more stable, then the reaction should happen. If entropy is also a factor, then you have to think about that. You have to worry about that to determine whether a particular reaction would happen or not. But for acid-base reaction, or we should say proton transfer reaction, that's easy to predict. And now what we want to do is, and then we also said that because it only depends on how stable the product is, it's a very strictly an equilibrium situation, right? And so because of that, if you know the pKa, which is an equilibrium constant, or one way to express the equilibrium constant, if you know the pKa of a particular proton, you actually get to find out or predict whether a particular reaction happens or not. So in this section of the chapter, what we want to do is to talk about different functional groups and their corresponding pKa's. Okay? And because the acidity of a particular hydrogen largely depends on the functional group that it's attached to, because the pKa of a proton is fairly inherent to the functional group. Okay, so in other words, and then the functional group kind of dictates how stable it is once it loses a proton. So what I want to do here is to sort of make a table, and these are some of the pKa values for a typical functional group that I want you to know actually by heart. Okay, so let's start with something really extreme, like alkane. That's butane. We would usually never think of that as something acidic, any hydrogen off of this alkane, and so for that reason you would expect the pKa to be really, really large or small? Large, right? So then, thank you for like one out of like the whole class of you that actually said large to the YouTube video, you know, and answered my actual question. Kudos to you. Right. So that would be about a pKa of 50, because this is not at all acidic. Where the next one on the ranking, so this is in the order of increasing acidity. Here's an ammonia proton, and this hydrogen here is what we're talking about. That would be around 36. So again, this is not very acidic either, because if you think about the conjugate base, that's very not all that stable, because nitrogen is not, it is electronegative, but it's not all that electronegative, and it's even worse if it's a carbon, right? If you look at the conjugate base, that's very, very not stable. So, but if you go up to the alkyne here, that is actually fairly acidic, this proton. Thanks to the fact that, remember, we said that sp3 carbons are a lot more electronegative than sp3 carbons, and so because of that, this sp carbon can stabilize in the conjugate base. So this is around pKa of 25. This negative charge is a lot more stabilized by the carbon, more so than, say, if you were working with an alkane. And so for that reason, that's fairly large. And this, also in an alkyne anion here, what happens is, it's called acetylide ion, by the way, but this anion is not it's not next to very many other electrons, right? Because of the linear structure, linear shape of this alkyne anion, it's not next to very many other hydrogens. Whereas in an sp3 carbon, those lone pair electrons have to actually sit next to these electrons in carbon-hydrogen bonds, so that destabilizes this excess electron density. But there's nothing like that here, so that's not a really horrible, or this is a lot more stable of a conjugate base than that, and that's reflected in the pKa. Another one I want you to know about would be an alcohol, or really any type of OH group, including, I would say, water is similar in pKa to this. Okay. And this is around 16. Another alcohol would be a phenol. This is an alcohol, but because, as you can imagine, the conjugate base of this, the negative charge on this oxygen, can be resonance stabilized by the ring. Because of that, this is a lot more acidic, pKa of 10. And now, if you had the ammonium ion, so it's not ammonia, but like that, but ammonium ion with a positive charge, this proton would be even more acidic than that. But if you think about it, that's not so acidic, considering the fact that this ammonium ion is positively charged to begin with. You would think it wants to get rid of its hydrogen or proton to get rid of the charge, but it doesn't mind hanging on to this proton because, remember, nitrogen is basic. So that's reflected in the fact that it's a decent acid, but it's not so acidic. Okay. Continuing the table here. So it's acid, pKa. The next one up would be carboxylic acid functional group. As you might expect, it's getting to be a lot more acidic. Now this is around pKa of 4.7. And then the next one down would be hydronium ion. Now this oxygen does mind being positively charged a lot more than this nitrogen does in ammonia. And this is around negative 1.7. Now, you might notice that value is negative. What does that mean? That means it's actually a strong, very strong acid. For the most part, you could expect this to dissociate almost completely. Okay. And then, speaking of strong acids, this would be a really, really strong acid, and that's this sulfuric acid. This is around pKa of negative 9. And usually pKa's don't get any lower than that for the most part. Okay. So these numbers, perhaps at the moment, it might just be a matter of memorization, and that's always not something I like to recommend, but at least the ranking here, I think you can sort of rationalize that these acids up here, they're not acidic at all. These are very acidic. And the reason why I want you to know the pKa values of these is once you know these and you see other functional groups, like let's say you see this isopropanol, which is rubbing alcohol, by the way, you can sort of expect figure out what the pKa of this hydrogen might be, right? If you remember that alcohol is usually 16, you would expect it to be something in that range, and indeed it's around 16 and a half. It's a little bit different, but it's in the same ballpark, and that having that idea sort of helps you down the road in organic chemistry to predict the right sort of reaction outcome. When you see two molecules coming together, you can sort of tell what's going to happen. Likewise, even if you didn't know the pKa of water specifically, if you know that alcohol OH is around 16, you still see the same, essentially the same functional group here. And so you expect it to be around 16, and then indeed it's around 15.7, right? And then if you need to know the pKa value of this benzoyl benzoic acid that we actually used in the recrystallization lab, right? We said that it's somewhat acidic. Its pKa value, we would expect it to be something like this, 4.7. It's indeed around 4.2. So what's the point? Well, if you have molecules with the same functional group, they usually have similar pKas. Okay, so now that we know sort of what sort of strength of acid you would expect for each type of potentially acidic proton, pretty much in any molecule now, because if you know that table that we just talked about for the pKas and different functional groups, those are pretty much the only types of functional groups you would find really in any molecules that you would encounter, so that at least in this class. And so you should be able to sort of figure out what strength of acid you're dealing with just by looking at a structure. Now, I want to kind of throw this in there, the leveling effects, because just because some acid, like the sulfuric acid, is dissolved in some sort of a solvent, doesn't mean that this actually is the strongest acid, even though you might say, well, wait a minute, dude, sulfuric acid's pKa is 9, well, -9, I still remember that. And hopefully you still remember that, because to you that was only like a minute ago, right? And if you compare that against water's pKa is only like, what, 15.7, that definitely is the strongest acid you might think. But the leveling effect is this: when you dissolve a solvent, when you dissolve some really strong acid, but if the solvent that it's dissolved in can be protonated by that strong acid, that protonated solvent molecule or ion probably is going to be the strongest acid, because this reaction, once it reaches an equilibrium, this proton transfer, there's not going to be any of the strong acid left. All of the strong acid will have donated its proton to the solvent, so then the protonated solvent is going to be your strongest acid. So for example, if you dissolve sulfuric acid in water at equilibrium, what happens is the hydronium ion, that's going to be your strongest acid, because all of the sulfuric acid is much stronger of a acid than hydronium ion, so the equilibrium goes all the way to the right. So this is the only acid. So at equilibrium, which you can reach pretty much as soon as you mix the two. That's how fast proton transfer reactions happen. It's instantaneous. Hydronium ion is your strongest acid. So when we begin to start looking at mechanisms of reactions, I want you to remember this. If we ever use sulfuric acid in water, for example, in the reaction mechanism, which tells the story of how the reaction happens, that's the acid of the story, not sulfuric acid, even though that's where the proton came from, because of the leveling effect. And the equilibrium, of course, will go like this, at H2SO4 and water combined. Equilibrium is way to the right. Right, so that's the species unit. Even though we talked about the different pKas attached to different functional groups, and those usually cover most of the functional groups or molecule features you would encounter, it's still a kind of difficult once you're faced with a particular molecule or ion, and you have to know somehow the relative acid strength, or you have to estimate how strong of an acid that is exactly. So let's start talking about exactly how you would go about this, because this is an important skill that you're going to have as we try to understand different organic chemistry reactions, right? So is just a generic acid. How do you know how much of this generic acid, or hopefully we're going to be looking at a specific acid in a second. How do you know this specific acid is a strong acid or weak acid? Or if it's weak acid, how strong of a weak acid is it? What's the strength of the acid? How do you know? Well, the way you estimate that is by evaluating the conjugate base's stability. Okay. Well, how do you do that? Right? How do you estimate the stability? That's a good question. If you ask that, good job. How do you estimate conjugate base's stability? How to do that? Well, I had to just throw out a random rule acronym, but there is sort of an acronym for this. Maybe it helps you remember that. We're going to call it the CARI rule. And hopefully thinking through these rules becomes just sort of like a second nature to you, so that you don't necessarily have to rely on this memory tool to remember. But the C stands for charge, which is a bigger factor and more important than C stands for charge. That's more important than at the nature of the atom itself. And here we're talking about electronegativity. And here we're talking about whether your acid has a charge or not. If it has a charge, especially positive charge, there's a good chance that's a pretty good acid. If the atom that your proton is attached to is electronegative atom, there's a good chance it's a pretty good, pretty strong acid, because the conjugate base, which would be negative, would be fairly stabilized by its electronegativity. And then this is more important of a factor than resonance. So resonance is sort of third in importance, but it's still pretty important. If the conjugate base can have resonance, then it would be a very stable conjugate base. And this is now even more important than the inductive effect, but inductive effect is something that you still want to think about. Okay. All right. And so I stands for inductive effect. Inductive effect, remember, is the impact that some other atoms have, usually how much electron density they're pulling through bonds. That's inductive effect. Okay. So first, let's think about the charge. Factor. Okay. And the reason why this is the most important factor is because I think we kept saying this back when we talked about resonance, but the charge is very destabilizing. Okay. Right. So here's an acid, or potential acid. Potential base. And usually we don't really think of water as a good base, and it really isn't. But let's say we're going to just treat it like a base at the moment. Let's say water grabs this proton. What would we get? Well, we would get, here's our acid, here's a base. We would get the conjugate base, this species. base. Here's your conjugate acid. What's the point of showing this like really awkward reaction that really doesn't happen that much at all? Well, we started with a neutral species, neutral acid and neutral base. Maybe those are not very good descriptions of those two molecules, but we'll bear with it for now. Once the acid-base reaction or the proton transfer reaction happened, look at what happened. The conjugate base is now negatively charged. Conjugate acid is now positively charged. They both have charges now. That, remember, we just said is destabilizing. These are very unstable. That's not a very good product. What does that mean? That means the equilibrium lies far to the left because charge is very destabilizing. What does that tell us? So if you have to get a charge to do your proton transfer reaction, chances are that's not going to be a very good reaction. Okay, so that's what this tells you. So what was the point of that reaction? We show that we went from neutral species to charged species. That is really bad. That's a bad reaction. I put up the same reaction that we just looked at up there on the board. And here's another similar reaction, but here the difference is we start out as a charged acid with a neutral base, but in that situation the things look much different because remember charge is destabilizing. Here the reactant is actually kind of not stable. Because of that, if we start out with a not so stable reactant, the reaction actually happens rather well. So once the base, corresponding base might pick up the proton, here's what you get out of it. Right, we do end up with one charged species, but we started out with one charged species. So that's a lot better than starting out with two neutral and then ending up with two charged species, right? And so now to compare these two different acid reactions, proton transfer reactions on the same energy diagram, this is what it would look like. For the first reaction, we start out with a very stable, low energy species, but we end up with a really high energy species. So this is what it looks like. Right. Now, for the other one, between this and that, what happens is we start out with a fairly high energy species, and we end up with a fairly species of energy that's pretty similar to that. This is what the reaction energy diagram looks like. In other words, this reaction to get to the product, it has to overcome so much energy, but from here to there, it's really rather easy to get there. So this second reaction happens rather easily, and not the first one. Remember now, what we're trying to do is to understand how to use the CARI rule, and I guess we're trying to understand what the CARI rules are. We first covered that C for charge. Charge is bad. If you got a charge, you want to get rid of it. If there's that driving force to get rid of a charge, it's a pretty good asset. And if you have to concoct a charge to act as an acid, that acid is going to be a really bad acid because that you're going up an uphill there, right? In terms of energy. So that was C for charge. Let's think about A for the atom, or we're specifically really thinking about the electronegativity of the atom, but it's the A in the CARI rule. First, as an example, let's compare methane and ammonia as potential acids, sources of protons. So here's methane, ammonia. We just arbitrarily using water as the base. It really doesn't matter what we pick as the base because we're just comparing the acidity of these two. Okay, this is not a very good base, so it's not going to be. Neither of these are going to be good reactions, but one is going to be slightly better than the other. If methane acts as a base, that's your conjugate acid, or excuse me, conjugate base. if ammonia acts as a base, the conjugate, what am I saying? If ammonia acts as an acid, excuse me, the conjugate base is going to be this, it's called an amide ion, but NH2 minus, and of course the conjugate acid is still the hydronium ion. Okay, so hopefully no surprise there. We should be able to predict one of these is better than the other. Even if you didn't know the pKa of these two, I would say. If you do know the pKa for the alkanes, it's usually roughly 50, and in fact, the pKa of these protons is roughly around 48. pKa of hydrogen is roughly around 36. Okay. Now, so if you didn't know the pKa's, how do you know that one, obviously this is the better acid than that because of the pKa. How do you know ammonia is the better acid than a methane? Well, it's because of the electronegativity of the atom. If you compare these two conjugate base species, remember the way to estimate the relative strength of potential acids like these two is to actually look at the stability of the conjugate bases. Right, so here's your conjugate base right here. And we have a negative charge, and we want to compare the stability of the two. And if you think about it, nitrogen is more electronegative than carbon, and so for that reason, nitrogen is better able to stabilize this negative charge than carbon can. So for that reason, this is a lot more stable of a conjugate base than this methane anion here. So to compare these two reactions that we just talked about using an reaction energy diagram, or reaction coordinate diagram as it's called sometimes, it would look like this. I put both pairs of reactants basically at the same energy level because both of these pairs are neutral. When things are neutral, and usually they're fairly stable like that, so they're usually pretty low energy species, so they're roughly about the same energy levels. Okay, but there's a difference in these charged species. Well, hydronium ion is the same in both pairs of products, but the carbon is not as able to stabilize the negative charge as much as nitrogen can. So this is the lower energy reaction. So the two reaction diagrams will look like this. For one path, it will look like that. For the other pathway, the reaction energy diagram will look like that. Obviously, this is the much better reaction, even though still these are not great acids. So take home here is that the negative charge is more stable on nitrogen than on the carbon due to electronegativity difference. Therefore, we can conclude, even if you didn't know the pKa's, which I do want you to know. Oh, by the way, I forgot to mention, we're going to have an extra credit, but pKa quiz after we come back from the fall break. So please do study that pKa table. Basically, I'm just going to ask you what the pKa's of those species are. So this is a stronger acid. To compare the acid strength. So here we wanted to compare ammonium ion and hydronium ion. And again, the goal is for you to be able to use CARI rule sort of in your head, so that when you look at two different species, two things that are, let's say, in the same pot, as we say, in a reaction vessel, you know which is going to be the stronger acid, which means you know which species is going to donate the proton and which is going to receive the proton. Excuse me. Let's compare these two and see if we can use the CARI rule, in this case the A rule, to figure out which one's which one is the stronger acid. So if we, this time, instead of writing two different reactions to compare, I'm just going to sort of put these two in the same equilibrium. That may be at first a little bit confusing, but once you get the grasp of it, I think it's easier to understand. So I've already kind of wrote that equilibrium lies more to the left, and that's because you might still recall what the pKa is for each of these things. The ammonium proton, pKa of that is around 9, right? And then the pKa of the hydronium ion, if you remember that, is around negative 1.7. Okay. What does that mean? That means that this is the stronger acid than that, which means this is the acid that is going to dominate in terms of donating a proton. And this is not going to dominate. It's the less of an acid. So that means, what does that mean? That means this is going to donate its proton to go to the left. The equilibrium lies to the left, meaning the hydronium ion is stronger than ammonium ion. That's what we're saying here. But to put this into the reaction energy diagram, right, this is what it's going to look like. What we're saying is this time the product is sort of similar energy level, because both water and ammonia are not charged. It's neutral species. They're pretty stable, so they're going to be down here. And what we're going to say is hydronium ion sort of starts out at a higher energy level than ammonium ion. That's our prediction. Why? Because, once again, the electronegativity. Oxygen is more electronegative than nitrogen is. It's more greedy. It's greedier for electrons. So the worst thing that can happen to an oxygen is if it's positively charged. Nitrogen, on the other hand, it's not as electronegative, so if it has to be positively charged, that's not the end of the world for nitrogen. So this is more stable, so less energy. This is less stable, higher energy, because it's hard for oxygen to have that positive charge, and so for that reason, the energy diagram will look like that for the hydronium ion. For the ammonium ion, energy diagram will look like that. Hopefully you can see that. I'm not sure. The top one, I'm just going to use green, like so. So which one is the easier reaction to do? Well, I want you to, when you compare these two, this top reaction actually is the better reaction to do than this reaction. Why? Because you gain so much energy. There's so much more energy gain when you go down from high to low, right? Just remember, this is like, enthalpy is like going down a slide, right? You get a lot more momentum going down a taller slide than a less tall of a slide, right? So to summarize the comparison between these two reactions, we're saying that the positive charge is less stable on oxygen atom compared to nitrogen due to, once again, the electronegativity. So hydronium ion here is a stronger acid. Okay. So to finish our discussion on the A part of the CARI rule, the electronegativity of atom, using that to predict which acid is stronger and whatnot. Let's compare these three species: ethane, ethylene, and that's an alkyne called ethyne, right? For those of you who watched the video up to here, just Good job for actually staying in the video. This is my dog. He's helping me with the video lecture. Now, when you compare these three species, what is the only difference? Well, the only difference between these three species is really just the hybridization of the parent carbon. Right. Here we've got sp3, sp2, and sp carbon. And how do you know which is stronger acid and which one's less? Well, you might still remember the pKa of alkanes. You might remember the pKa of alkynes. If you do, that's great. But if you don't, what do? More importantly, on that one table that we talked about, how you should memorize it, at least for now, we didn't even list an alkene proton, right? Like sp2 carbons, hydrogen. That wasn't on the table, so how do you know which one's stronger and whatnot? Well, remember the rule of thumb in determining the acid is you look at the conjugate bases stability. So let's think about that. If these things lose the protons, what do they become? Well, this will become this conjugate base. It looks like that. If an alkene loses a proton, it will become this conjugate base, and then if an alkyne loses a proton, it would become a conjugate base like that, where we have, let's think about the hybridization of this carbon. It's got 1, 2, 3, 4 things in 4 different orbitals. So you need 4 equal orbitals, and to do that it needs to be sp3, so that's an sp3 carbon. And this has 1, 2, 3 things attached to it. It's an sp2 carbon that has a negative charge, and here's of course an sp carbon that has the negative charge. If you recall, when we talked about the difference between these differently hybridized carbons, remember sp carbon is 50% S in character. sp3 carbon is only 25% S in character. What's the big deal? S orbital is very tiny and compact. So sp carbon is a lot more compact of an atom than sp3 carbon is, so to speak. And so for that reason, electrons in sp orbitals, they tend to be a lot closer to the nucleus where there's more positive charge. And so for that reason, sp carbon effectively has sort of a higher electronegativity that electrons around it experience than, say, sp3 or sp2 carbons do. So what we're saying is that this carbon, for instance, has the highest effective electronegativity. Meaning that this sp carbon is most able to stabilize negative charge. Can you see that okay? Yep. You know what, I just realized I haven't been using my most amazing teaching tool, the finger. So between the three, right, this is the most stable conjugate base because sp carbon is able to stabilize a negative charge more so than sp2 or sp3, and in fact it goes in that order: most stable, less stable, least stable. And so if you compare the acidity of the three potential acids here, this is going to be the most acidic. Alkane, of course, is going to be the least acidic, and that's reflected, of course, in the pKa. This is around 50. The pKa of an alkene proton is around 45, and alkyne proton, you still might remember that it's around 25. So let's think about the impact that resonance has on the relative acid strength. Okay, if you get the first two, C and A, charge and atom, resonance, it gets a lot easier to understand, because here we're only talking about the stabilization of the conjugate base through the pi bonds, right? So here's a good pair to compare. Here's an alcohol that, of course, is a carboxylic acid. We're using the same base, so that's a fair comparison. And which is going to be a better reaction, or a better way to say it, which is going to be the better acid? You might already know, even just based on the functional group name, that that's probably going to be the better or stronger acid. But let's just sort of prove this to ourselves using the resonance idea. Okay. Remember, to compare the relative acid strength, you always want to look at the conjugate bases. Right? So let's draw the conjugate base of those acids first. Here's the conjugate base of the carboxylic acid. When it becomes conjugate base, it's called a carboxylate ion. Of course, carboxylic acid, right? Now this does have resonance. Why? Because if you've got a negative charge, lone pair next to a pi bond or double bond. So here's the resonance. Right, that these electrons So that's your two resonance structures. What does that mean? That means the negative charge is not localized to this one oxygen, but it's delocalized between the two. So the two oxygens actually get to share the burden of having a negative charge. Remember, charge is destabilizing. It's a bad thing. That's like having a credit card charge. That depresses me, talking about debt. But, oops, wrong color. Here's the product with both hydronium ion here and here. If you draw the conjugate base of the alcohol, it's going to look like that. Right, that's your conjugate base. And this, unlike a carboxylate ion, this is called alkoxide ion. When you get a conjugate base of an alcohol, that's called alkoxide ion. Of course, hydronium ion. It's the other products when water acts as a base. But if you look here, that's a sad situation because there is no resonance. There's no other oxygen friend to bear the burden of the negative charge. This is no resonance. What does that mean? Well, that means this. If you compare the pKa of the two, right? Here's pKa of 4.7. This is pKa of around 16. And you might have just remembered that anyway. So that makes sense that that's much stronger acid, but based on the resonance idea, it makes sense even without knowing the pKa's, because here the conjugate base of carboxylic acid is resonance stabilized. It's a lot more stable, so we expect that to be much stronger of an acid. Okay, so this is your stronger acid. And that's because the conjugate base is more stable. Okay. All right, finally, let's talk about the I in the CARI rule, which is in the inductive effects. And it's really, I think, convenient or useful to compare this to the resonance effect. Resonance has to do with stabilization through pi bonds, because through pi or p orbitals, electrons can delocalize. But if all you have is sigma bonds only, no resonance, you still can have a little bit of stabilization through the sigma bonds, even though there's no resonance. if you have something called electron withdrawing group somewhere in your molecule, hopefully nearby that proton that is supposed to be the acidic proton. What is an electron withdrawing group? It's just any group that is electronegative enough that pulls electron density towards it from away from something else through the bonds. Okay. As opposed to electron donating group, that's what EDG would stand for. This would push electron density through the bonds. Okay. So for example, if you compare the two, right? Which one should be the stronger acid? Well, let's think about that. How do we do it? By now you should know we compare the conjugate bases, right? After it loses the proton to some sort of a base. Okay. Here we're not going to even omit the base because I think we've done that plenty of times. Here's the conjugate base. It's going to look like that. Both are actually alkoxide ions. But what's the difference? In the alkoxide ion from ethanol, it's called actually ethoxide ion. There's no electron withdrawing group. Rather, these are sort of electron donating groups because carbons and hydrogens are somewhat electron rich and they're not very electronegative. They're sort of giving as far as electron density goes. So this sort of has an electron donating group, whereas this trifluoroethanol or trifluoroethoxide conjugate base, right? This has an electron donating group because this carbon has 3 of the most electronegative atoms in the periodic table here, right? So this is an electron withdrawing group. This, you could sort of say, an electron donating group. I mean, it's not a very strong one. So which one is the better acid or a more stable conjugate base? It would be this because electron density is sucked away towards the trifluoro group, right? There's a polarity towards that, and because of that, this oxygen experiences sort of less of a negative charge than that oxygen would. So for that reason, this is the more stable of a conjugate base. What does that mean? That means this should be the stronger acid because its conjugate base is more stable. So to put that into words, we could say that a part of the negative charge is withdrawn by the fluorines. Inductively. The word inductive just means to pull through something. So the electron density is sucked away through the sigma bonds. That's inductive effect. So this is now stabilized. Okay. And that is again reflected in the pKa's if you compare the actual experimental pKa. This you would know by now. The pKa is, thank you very much, it's 16. Right. The pKa of this, we may not know experimentally off the top of our heads, of course, but you should be able to predict what kind of number we should get. Is it going to be lower or higher than this? It should be lower. It's the stronger acid. And indeed, the pKa of this is experimentally 12.4. And that, again, is due to the inductive effect. So now that you know all 4 components of the CARI rule, you should be able to look at a number of different potential acids acids and compare their relative acidity. And that ranking of acidity is a skill that I want you to have. And so for that reason, when we come back from the break, we're going to apply these CARI rules to different acids and rank their acidity together. Okay. Have a nice break. God bless you. Love you guys very much. Stay safe. We'll see you in a week. Here's a little bonus segment of the video. I don't know if you guys knew this or not, but I have a little bed for my dog Asher, and he's apparently organic chemistry lecture is not that interesting to him because he fell asleep.